Welcome back. In this video we are going to analyze and to make a proof of the fundamental theorem of calculus. The theorem says, consider a function f, little f, that is continuous on the closed interval ab. Capital F is the antiderivative of f. So the derivative of f, capital F, is little f. If f is the antiderivative of little f, when you make the integral from a to b of f of x, so you find the area from a to b of little f, the area can be found by going to the antiderivative of the function and find f of b minus f of a. F of b will be like this, all these things, and f of a will be like this in a way that f of b minus f of a is more or less this change, f of b minus f of a. So what is the connection? Why the area is related with the change in the antiderivative? To understand the proof, we have to say something before doing the proof. Okay, these are the preliminary details. You see, imagine this is the function capital F. The function increase, the slope is changing. Imagine that I consider the point x sub c that belongs to the interval AB, so I divide the interval AB in many subintervals, and one of the subintervals is from x sub c to x sub c plus 1. Now, this is f of x sub c, and this is f of x sub c plus 1. So this is f of x sub c, and this is f of x sub c plus 1, everything. What is this part? This small part is f of x sub c plus 1 minus f of x sub c. Everything minus this is this part. So I will see the triangle here. The triangle says that this is f of x sub c plus 1, and this is f of x sub c. Perfect. So the triangle is here, is this small triangle, and the change in the function, in the capital F, is f of x sub c plus 1 minus f of x sub c. Now let's go to the same point x sub c. So the slope here, the function f of x, represents this value of the slope of this function of the capital F. Here I see the slope 0. So the function f of x, little f of x, will say 0. Here I see the slope a little bit big. So the slope will be a little bit big. Little f represents the values of the slope. As I'm moving to other x, the value of the slope grow up, so it has to be something like this. The value of f have to grow up. F of x is the value of the slope of capital F. Okay, so now let's pay attention to the area under the curve of little f of x. The area under the curve of little f of x is this area, is the value of the height, the f of x sub c, multiplied by the width. F of x sub c by delta x is the small area that are here. Now, f of x sub c is related with the slope of capital F. So f of x sub c is the derivative of capital F respect to x at the point x sub c. So the derivative of f respect to x at the point x sub c multiplied by delta x, this is the small area. but the derivative of x, the derivative of f respect to x at the point x sub c is more or less f of x, the limit when delta x tends to 0, but it's more or less f of x sub c plus delta x minus f of x sub c divided by delta x. And multiplied by delta x is the change in the function little f. So this is what we have to see, that this chain that is here, the chain that is here, this chain, this small change in the function is equal to the small area that is here in little f. This is what we have to see. Let's go to the proof, but before we need to remember some preliminary thing. That is the mean value theorem. Okay, the mean value theorem says that for functions that are continuous and differentiable on interval AB, there is a point C inside the interval AB such that the slope of the curve, this is the slope of f, is equal to the slope that connects the point A, capital A, with the point capital V. So the slope of this rectilinear line is the same slope that this one for some point C. So what it says that exists C such that f prime of C, the derivative at the point C of the function, is f of b minus f of a divided by v minus a. Is the slope that connects the point capital A with capital V. If you put the point V, for example, here, let's say that B is here and A is here, so the rectilinear line that connects capital A with capital V will be this one. And what it says that exists some point C whose slope is parallel, is the same slope than the slope that connects these 2 points. Now the point C is now here. You cannot, C prime, let's say. So you cannot avoid whatever is the point. If f is continuous and differentiable, you cannot avoid this theorem. And this theorem we will use to prove the fundamental theorem of calculus. We will use it. Now let's go to prove our fundamental theorem of calculus. We have the function capital F, the antiderivative. We have f of a. We have f of b. We have the chain in f from f of a to f of b. What is the chain in f from f of a to f of b? This thing, this length. The length, this is f of b minus f of a. And what is f of x sub 2 minus f of x sub 1? F of x sub 2 is this half. F of x sub 1 is this half. And f of x sub 2 minus x sub 1 is this small change in the function. What is f of x sub I plus 1? Let's say x sub I plus 1 here. X sub I plus 1. What is f of x sub I plus 1? Minus f sub x sub I. Let's say that this is f sub x sub I. So the chain is here, is this part of the triangle. This is the subtraction of f sub x sub I minus f sub x sub I minus 1, this part. the sum of all the changes is f of b minus f of a. So what I'm going to write is f of b minus f of a expressed as the sum of all these small changes. All these small changes. So no one will discuss with me that if I add something to an expression like this, and if I subtract and add, nothing will change. So the game here is subtracting and adding the same thing. So I'm pairing, subtracting, adding, and pairing. So I subtract a term, I add another term, and I pair the first one. Now I do the same with the, well, now I have paired the first term. And I have this expression, which is f of b minus f of a. Let's go to introduce another term by adding and subtracting. I have the term f of x sub n minus 1, and I want to subtract the term f of x sub n minus 2 and add it. So I have not done anything. Minus f of x sub 0. Now I pair it. And now I do it again. Let's go to right again. F of x sub n minus f of x sub n minus 1 plus f of x sub n minus 1 minus f of x sub n minus 2 plus, now I start with f of x sub n minus 2, and I subtract f of n sub n minus 3 and add it, f of x sub n plus 3, and nothing has happened because I have add and subtract the same thing. So now what happened? I pair it. I pair it. I pair it. Now it appeared the change, the small change in the function when the function moves from x sub n minus 1 to x sub n, plus the small change in the function when the function change from x sub n minus 2 to the following point, x sub n, plus the small change in the function. And like this, I can create all these changes, all these vertical changes, all these small changes. I can do it in the limit when delta x tends to 0, and when I sum all the changes, what will happen? Well, let's go first to divide this expression. Every parenthesis I will divide by delta x, and I will multiply by delta x. Later on, I will take the limit when delta x tends to 0. So what will happen? What will happen here? I'm writing incorrectly this. If f evaluate at the point x sub n minus 2. Okay, f sub n minus 2. Now, if I divide by delta x and I multiply by delta x, and I take the limit when delta x tends to 0, this is the derivative of the function at some points between x sub n and x sub n minus 1. So this is the derivative of capital F, which is little f, at some point c in between the interval x sub n x sub n minus 1 to x sub n. So it will appear the sum of all these terms, delta x. And what is the sum of f sub c sub I by delta x? This is the Riemann sum. This is the integral of f of x by d dx. So what I have proved that the integral from x equal a to x equal b, the infinity sum, is f of b minus f of a, being f the antiderivative of little f. Okay, to use the intermediate value theorem, but exists this c sub I whose derivative, the derivative of this, you know, here is f of x sub I, and here f of x sub n, and here is f of x sub n minus 1. So if I apply when delta x tends to 0, before delta x tending to 0, I can say, well, exists between here, the curve may be do like this, but exists a point C here in the interval whose slope is the same that the slope, that this slope. So when I take the limit when delta x tends to 0, the value of the limits is the derivative of f, capital F, at the point in the interval. And this is the derivative of capital F is f sub c. So as a conclusion, well, I have to use, I forgot, we have done the proof, because if f prime sub c sub I is f sub c sub I, and delta x sub I is the difference, is the interval, is the distance, is the length, the width of the subinterval, x sub I minus x sub I minus 1, what we have proved that s sub b minus f sub a is the sum of s sub c sub I by delta x sub I. But this is the Riemann sum. This is the integral of f of x d dx from x equal a to x equal b. And the problem is solved. So this important equation tells us that we, by repeatedly applying the mean value theorem in every subinterval, you can always find the collection of points C sub I such that the constant f of b minus f of a will be the Riemann sum of the little f on the partition AB. The theorem says like this. Don't do the Riemann sum, look for the antiderivative of f, and look for f, capital F of b minus capital F of a will give you the sum, the Riemann sum of the integral. Well, I'm sorry that was too long. I hope you catch all the ideas.